Welcome to this lecture series in real analysis. This is going to be a very important lecture where we will talk about the continuity of the inverse of a bijective continuous function. First, we will see that it is not always true, meaning there are bijective continuous functions whose inverses are not continuous, but then we'll see a sufficiently general class of functions which satisfy that property. And then as a result, we'll show, as a corollary, we'll show that the surds, meaning in particular, if you take the square root map, for instance, the map which takes x to root x, or the map which takes x to cube root x, or fourth root or fifth root, and so on, all these maps are continuous. Something that is intuitively obvious, but it is hard to prove, or is at least a headache to prove using first principles. Okay, so let's recap some basic things that we will need. So fix an interval I, and suppose we have an injective continuous function defined on the interval I, then the function f is strictly monotone, meaning either it strictly increases or it strictly decreases. We proved this, and also recall that the image of I is an interval. We proved earlier that the continuous image of any interval is again an interval. This was the result of the intermediate value property. Okay, let's recall the convergence criterion of continuity. Suppose we have a function from a set S to the reals, where S is a subset of reals, and assume this is So we are given such a function, and we say, or equivalent, or what should I say? Then we know that f is continuous at x naught if and only if whenever this thing is a sequence in S, meaning the domain of f, such that the sequence converges to the point x naught, then the image sequence converges to the image of x naught. So that's the criterion of continuity via convergence. So we know this, and if you take the contrapositive, immediately, well, you will not see this immediately, but let me read out. This is very important. So fix a function from a set S of real numbers to real numbers, and fix a point y naught in S. I'm changing notation. Previously I had used x naught, but there is a reason why I'm using a different symbol. So fix a point y naught in S, then the fact that f is not continuous at y naught, so if we are given that f is not continuous at y naught, implies immediately from this criterion that there is a sequence in S which converges to y naught, and there is a positive epsilon such that this happens frequently, right? Immediately from this criterion you can deduce that. Why can you deduce that? If this function is not continuous at y naught, then there must be a sequence of points in S which converges to y naught, but the image sequence does not converge to fy naught, which means that there is some epsilon for which this thing is not bounded by epsilon frequently, meaning this happens frequently. However, in this statement I've written for all, I haven't written frequently. Doesn't matter. Once you found a sequence where this thing happens frequently, you can extract a subsequence of yn where this thing happens always, and that subsequence will satisfy this, So please note that this is a fact, very simple fact, but we will use it, and you should stay on it. If it is not clear, then you should stay on it. Okay, here are some problems for practice, and now let us get started. So first we will see an example of a bijective continuous function whose inverse is not continuous. Okay, so we have a function defined on this thing to that thing. The definition is fx takes the value x in this region, and it takes the value x minus 1 in that region. So let's draw the graph. from 0 to 1. It looks like that. And I'll make a hollow circle there because 1 is not there in the domain. So you take a point here. I mean, I don't think this is an accurate figure. Yeah, okay. So you take a point here, you go up, you go there, that's the value. And 1 is not in the domain. So I make a hollow circle there. What about 2? I mean, this much is in the domain and that thing is in the domain. So now we will come to 2. What is the image of 2? The image of 2 is 1. So it's that point. And the image of 3 is 2. So it's roughly that point. And that is what the function is going to look like. I'll make a solid circle to indicate that this point is in the graph. This point is in the graph. This is not in the graph. Okay, so that's the image, or sorry, that's the graph of the function f. And clearly f is a continuous function because, I mean, it's continuous on this part and it's continuous on that part, and those are disjoint intervals. So you can convince yourself that f is a continuous function. That's a simple exercise. What about the inverse of f? So the image of f, first of all, is the entire interval 0 to 2. Yeah, so note that f is a bijection. That's one thing. F is bijective and continuous. Okay, so since it is a bijection, we can talk about the inverse of it. And the inverse has this as the domain, the entire 0, 2 as the domain. And let's see what is the inverse. So, yeah, let's try to draw the graph. So as I choose values here, 0 to 1, it's as good as choosing values here and picking the point which map to it. So in this region, it will map that way, just the line y equals x. Difficult to draw an accurate figure, but I guess this will have to do. And when I'm choosing the point 1, I get 2 as the image. So the inverse image of 1 is 2. Okay. And as I choose points higher than 1, I get these values. So they will map to that. Okay, I can only hope that the figure is accurate. So we see that this is the graph of the inverse, and clearly this is not a continuous function. This is, if this were a continuous function, then since it is defined on an interval, the image of the function would also be an interval. But the image of this function is not an interval because it is broken. We see nothing here is available. So it is clear that the image of f inverse is not an interval. In fact, it was clear from here itself. F is a bijection. The image of the inverse is this much, which is clearly not an interval. It's a broken part. It's a broken thing. Okay, so we have a bijective continuous function whose inverse is not continuous. All right, but as we'll show, all is not lost. If you have a bijective continuous functions whose domain was an interval, then the inverse would also be continuous, and that is the main result of this lecture. All right, so before we go there, we need to talk about something that was given as an exercise earlier. Suppose we have a compact set of real numbers, and we have a continuous function defined on that compact set. Then the image of it under f is also compact. So continuous images of compact sets is compact, and this was given as an exercise earlier, but since we will use it now and it is sufficiently important and not immediately obvious, I felt that I should also provide a proof. So let me try to just do this very quickly because this was an exercise. So I will not be writing in real time. I have already written a proof. Let me just keep showing line by line. So we start with an open cover of the image of A under S. And we want to show that this thing has a finite subcover. That's what it means to show that something is compact. You start with an open cover and show that it has a finite subcover. Meaning what? Meaning you show that there are finitely many things in J such that the corresponding V alphas contain f of A. So yeah, also recall, by open cover we mean a collection of open sets whose union contains the given set. Okay, so just recalling kind of the definition of compactness. All right. And here is the main point. Since f is a continuous function, we showed earlier that you take any open set and take its preimage that can be written as the intersection of an open set with the domain of the function. Right? So if f is a continuous function, nothing to do with the compactness of A. If f is a continuous function and you pick an open set V contained in R, then f inverse V is equal to U intersection A for some open set U. So this is what we showed, and if this is throwing you off, then you can go to the lecture about continuity via neighborhood. Okay? So for each alpha, we consider the preimage of V alpha, and we can find an open set U alpha such that this preimage is equal to U alpha intersection A. Okay, so just please note this point. And now we can define this thing. It's the collection of all the U alphas that you get. And clearly this is an open cover of A. Each U alpha is open. By choice of U alphas, each U alpha is open. And collectively they will contain A, because the preimages of each V alpha, if you put them in a set, that is a cover of A. V alphas form a cover of Fa, so F inverse V alphas will form a cover of A. Not an open cover of A, because F inverse V alpha may not be an open set at all. So they form a cover of A. Therefore these form a cover of A. And if these form a cover of A, clearly these will form a cover of A, because each of these guys is contained here. So also please make sure that you appreciate this point, that this is an open cover of A. And now by compactness of A, we can find finitely many indices in J such that the corresponding U alphas cover A. So we have this containment. And now to finish the proof from here, let me just write this above containment in a different way. Let me write it as follows. In fact, it's equivalent to the previous one. Saying this is equivalent to saying that. Or maybe not equivalent, I don't know. I don't want to think about that. So it at least implies that much. So now this means, since these are all subsets of the domain of F, and together they exhaust the domain. In fact, now this becomes equal. This is an equality now. So together these are subsets of the domain whose union is the entire domain. So their images will be such that the union of all the images of these guys will be the entire image. So this means that this is the entire image, right? Just purely set theoretic fact. But what is this thing? Since F inverse V alpha is that guy, F of that guy is V alpha, or at least is contained in V alpha, not equal to V alpha. That is wrong to say, but this is contained in V alpha. So I don't seem to have enough space. How do I do this? Right? So each of these guys, this is contained in V alpha 1 ... this is contained in V alpha k, just by virtue of that equation. So this implies that contains f of A. This is contained in V alpha 1, that is contained in ... V alpha k. So this whole thing is contained here, but this whole thing is equal to that. So this thing is contained there. And we have located finitely many indices such that the corresponding V alphas contain f of A, and this is what we wanted to do. So that proves that FA is compact. Okay, so this was an exercise, but I've done it in full. The important corollary that we need to take away from here is that if we have a continuous function from a compact interval, meaning a closed and bounded interval, then its image is also of the same sort. Why? Because first of all, the image of an interval under a continuous function is necessarily an interval. That's by the intermediate value property. And second, since this is compact, the image is also compact. But the only compact intervals are intervals of this sort. Closed and bounded intervals are the intervals of this sort. So the image of a comma b under f looks like this for some c and d in R. So this is what we need to take away from here. Okay. So now for one of the main theorems that we want to discuss. Suppose we have a function f from a closed interval to R, and assume that this function is injective and continuous. And let J be the image of the domain of f. Then we want to say that the inverse of f going from the image to real numbers is also a continuous function. So in this special case where you have the domain of the function as a closed interval, the inverse of an injective function defined on it is also continuous. So f is an injective function and hence a bijective function when you restrict the target to the image, and therefore you can take its inverse, and the inverse can be thought of as a function from J to R, not just I, but we are just writing R because we are comfortable when we look at R in the target. Okay, so I am sure you understand what this statement means, and now let us try to prove it. So we will go via the convergence criterion. Let us fix the point. Yeah, so before we go there, we may write J equals C comma T for some C and D. This is what we just proved, that the continuous image of a closed interval is again a closed interval. Okay, so we have that, and now let us fix a point in J, and in the figure I am denoting that here, and let yn be a sequence in J such that yn converges to y0. What we want to do is, we want to show that this thing converges to f inverse y0. That is the convergence criterion for continuity. You want to show continuity at an arbitrary point. You take a sequence in the domain converging to that point, and the image sequence should converge to the image point. So once we do this, we will be done. Okay. So we will write this thing as xn and that as x0. And let me also kind of denote things in the figure. So here we have x0, and let me also maybe draw one thing for yn. This is yn, maybe a different color would be better. And this is xn. Okay, so yn is converging to y0. We want to show that xn converges to x0. So suppose not, we are going via contradiction. Suppose not, then there exists epsilon greater than 0 such that the distance between xn and x0 is greater than epsilon frequently. Right? So that is the meaning of not converging to the point x0. And here is the kind of thing that we recalled in the beginning. I thought that I will be using exactly that statement that we wrote, but now I realize that we won't be using that statement as such, but whatever we said there will help us understand what we are going to say here. Okay. So Yeah, so we have that, and here is the thing. So passing to a subsequence, we may assume that, or let me not overcomplicate things. Let us just find a subsequence. So let this be a subsequence of xn such that the difference between, or the distance between x and k and x naught is greater than epsilon for all k. Why can we do this? We are given that this happens frequently. If this happens frequently over n, you can extract a subsequence where this happens always. So just make sure you understand this point. Okay, we have that. Fine. And here is one more thing that I want to write. I mean, I could extract a further subsequence, but here I want to say and x and k is convergent. Why do I have such a thing? This much was clear that I have that. Why can I write this further thing? Well, because I would extract a further subsequence of it which converges. Every bounded sequence has a convergent subsequence. This is called the Bolzano-Weierstrass property. I have a sequence with some property. I can extract a subsequence of it which converges, and this property will not change under that extraction. So I can, instead of doing those two steps, I can just write this in one single step. So it's very important to appreciate this deduction. Okay. So now say x and k converges to a point P as k goes to infinity. Okay. Since it is a convergent sequence, it has some limit. And since this is a closed interval, a comma b is a closed interval, and each x and k is in a comma b, the limit will also be in a comma b. Fine. Now by continuity of the function f, we get that fx and k converges to fp as k approaches infinity, which implies, by notation it implies, alright? So since this happens and f is continuous, we must have that. But by definition, fx and k is y and k. So y and k converges to fp. But y and k, as k varies from 1 to infinity, is a subsequence of yn, right? This thing is a subsequence of yn. Yn already converges to y naught, and hence this thing also converges to y naught. But this thing is converging to fp. So fp is equal to y naught. Fp must be equal to y naught. But then what is p? Since f is injective, there is only one point in the domain, there is only one point in a comma b that can map to y naught. F is injective. So p must be equal to x naught, because x naught maps to y naught, and p also maps to y naught. So p must be equal to x naught because f is injective. So the deduction is that, which means that x and k converges to x naught as k approaches infinity, because p is the limit point of the sequence x and k. But that contradicts this statement. This is converging to x naught, but at the same time, it is also away from x naught by a positive epsilon. So this is a contradiction. This is statement and that statement are in contradiction, and therefore we have proven continuity of f inverse at the point y naught, and we are done. It's an interesting piece of reasoning, but not at all a hard piece of reasoning. Okay, so that's very nice. The pathology that we saw in the beginning of the lecture does not arise if we have a closed interval as the domain of a function. So now naturally it leads to the question, what if we replace this with just some arbitrary interval? Does the same statement still hold? And indeed it does. So we have some continuous injective function defined on an interval I. Let J be the image of I, and note that J is also an interval. We proved it in the lecture on the intermediate value property. Continuous image of any interval is again an interval, maybe of a different nature. Open interval may not map to an open interval under an arbitrary continuous function, but it will be an interval nevertheless. So J is an interval. Assuming I is an interval, of course. We are assuming I is an interval. So then the inverse, which you can again define because f is injective and hence the function going from I to j is bijective, so one can talk about the inverse. This thing is again continuous. And here I don't want to give full details. Let me try to explain the thing in this figure itself. Maybe I'll draw a bigger figure. Let's see if I can explain it. Okay, so we want to show that f inverse is continuous. So we pick a point arbitrarily in its domain. So let y0 in J be fixed. And there are, well, before we go there, since f is an injective continuous function defined on an interval, it is a strictly increasing function or a strictly decreasing function. F is a strictly monotone function, so either it is strictly increasing or strictly decreasing. We may assume that f is strictly increasing because the argument when f is strictly decreasing is very, very similar. So we will assume that f is strictly increasing. Okay, and y0 is a point chosen arbitrarily in the domain of f inverse. Okay, so let's say x0 is S inverse y0. In other words, x0 is the point in I which maps to y0 under the function f. Since f is injective, there is only one point in I which maps to y0, and we have called that point x0. Let me draw that. Okay. Now there are two cases. Case 1 is that x0 is in the interior of I. Let's recall what is meant by interior. So if we are given a subset S of real numbers, then interior of S is defined as all those points in the set S such that there is a neighborhood containing this point contained in S. There exists a neighborhood of Y, neighborhood U or V of Y, such that V is contained in S. So I'm just recalling the definition of interior. The idea behind the notion of interior was interior of S is the largest open set contained in S. Anyway, so there are two cases. Either x0 is in the interior of the interval I or it is not in the interior. Let me only argue in this case, the case where x0 is on the boundary of I will be left as an exercise. Okay, so if x0 is in the interior, then there is some open interval around x0 which is contained in I. Let me draw that. Let's say this is an open interval around x0 which is contained in I. In fact, I may assume that there is an entire closed interval around x0 that is contained in I. If there is an open interval contained in I, then you can just kind of trim it a little bit and obtain a closed interval containing x0 that is contained in I. And this closed interval is such that the endpoints are both distinct from x0. Okay? So this is on the left of x0, this is on the right of x0. Let's call this a comma b. This is point A, this is point B. So just to keep recording what I'm trying to say, A comma B has been chosen such that A is less than X, not is less than B. And we of course have this. Okay, and by what we have learned, we know that the image of this closed interval A comma B is again a closed interval. And we may call it C comma D. what we are saying is that f of a is equal to c and f of b equals d. And we know that this thing is going to map to a closed interval, and we have just recorded that here. So let me kind of draw it. Okay. So what we have is this restriction is a map from a comma b to c comma d. And this is a bijective continuous map on a closed interval. So its inverse is continuous. And its inverse is just, well, the notation for it is this. This is a map from c comma d to a comma b. And this is nothing but same as S inverse restricted to c comma d. So this is something that you should prove for yourself. And instead of a comma b, I will write r here. And I could have written a comma b, but I'll write r. So this is a continuous map, and hence this is a continuous map because they are exactly the same maps. So what we have argued is that there is some closed interval around y0 where these 2 points are strictly different from y0. Since a and b were different from x0, c and d are different from y0. Since a is less than x0, c is less than y0, because we are assuming that f is strictly increasing. And since b is greater than x0, d is greater than y0. So this picture is doing justice to the mathematics. Okay, so this is a continuous function, and hence this is a continuous function. The inverse, just give me one moment. The inverse restricted to the open interval c comma d. This is continuous. Since this is continuous, this is of course continuous. It is just the restriction of a continuous function. So f inverse is continuous in a neighborhood around y0, and therefore the function f inverse is continuous at y0. Continuity is a local property. If you can show that, given a function, if you can show that it is continuous in a neighborhood around a given point, then the function is continuous at the given point. So this shows that the function is continuous at y0, meaning f inverse is continuous at y0, and we are done. So this case is settled, and the other case, as I said, is an exercise. So that gives a proof of this theorem, modulo the remaining case, and that, as I said, is an exercise. All right, so we can move on now and see some applications. We have this function going from positive reals to positive reals, which takes x to the nth root of x. N is some positive integer. So you take x to the nth root of x. This is also a continuous function. This is not obvious. I think previously we established the continuity of the square root function. I don't remember if we did, but now we can just immediately prove it using the previous theorem. So how do we prove this? We have this function f defined on this interval, which takes x to the power n. And this is an injective continuous function whose image is this thing. And therefore, by the previous theorem, the inverse, which is nothing but x going to nth root of x, is continuous. So the nth root map is a continuous map whenever n is a positive integer. Very interesting deduction, even though this was expected. And you can show that if n is odd, then actually the map goes from the entire set of real numbers to the set of real numbers, and that is also a continuous map. If n is even, then one cannot define this map. For instance, if n equal 2, you can't take the square root of a negative number and obtain a real number as a result. So when you want to define a surd of a negative number, you better take the surd using an odd number. Okay, so we have these two very nice facts. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.